Swayam Prabha. Digital India. Educated India.
Welcome to the course on advanced machining processes. Today I am going to discuss with you about the anode shape prediction and tool design in electrochemical machining. Organization of the talk is: first I will give you introduction to the tooling design in electrochemical machining. Then what is anode shape prediction in electrochemical machining. After that I will discuss various approaches for anode shape prediction, including cos theta method. Then cos theta method will be discussed for tool design in electrochemical machining, and finally a very brief introduction will be given to the correction factor method suggested for tool design in electrochemical machining. Introduction to tooling design in electrochemical machining. Anode shape prediction and tool design in electrochemical machining are the two different problems. The first one, anode shape prediction, we are discussing about the shape finally obtained on the workpiece, and in the second one, that is the tool design in electrochemical machining, we are designing the shape and size of the tool so that we get the required shape and size of the workpiece. So, there are various methods that have been proposed by various researchers for workpiece, that is the anode shape prediction. First one was proposed by Tipton, and that method is known as cos theta method, very simple useful method. Second one, conducting paper analog method, which is more of experimental nature. Then Production Engineering Research Association UK proposed a method for anode shape prediction. Then various researchers have proposed empirical approaches for the prediction of the shape of the workpiece after electrochemical machining. This includes the prediction of the inter-electrode gap in various zones during electrochemical machining, as we will discuss in detail. Then after that we will discuss the nomographic approach for the prediction of the anode shape, and finally the complex variable approach that was proposed by Nielsen and Sui, that will be discussed. Later on, some of the researchers who had the interest in the numerical analysis approaches, they proposed finite difference method, finite element method, and finally the boundary element method was also proposed by couple of researchers from the England. Finite element method was proposed from India by Jain and Pandey, and finite difference method was proposed again from England by a group of researchers, which includes C.F. Noble. Then there are various approaches or methods that have been proposed for design of the shape and size of the tool, that is the cathode. The first one initially was proposed by Tipton, and that method is known as cos theta method for designing the tool. The second one is the complex variable approach, which was proposed by Nielsen and Sui, and this is more of theoretical nature. However, there was a big difference or deviation between the theoretical results and experimental results. Then the finite difference method was also proposed by a group of researchers from the Manchester, UMIST. Finite element method that was proposed from India by Jain and Pandey, and boundary element method again was proposed from the England by a couple of researchers. Tooling design in electrochemical machining, anode shape prediction, that is also known as analysis problem. The analysis problem deals with the prediction of work profile obtainable from a given tool while operating under the specified machining conditions. That means, machining conditions and shape of the tool are given to the operators, and what shape and size of the workpiece you are going to get can be predicted by various methods. On the other hand, design problem which decides or which designs the cathode or the tool shape. The design problem deals with the computation of the tool shape and size which under specified machining conditions would produce a workpiece having a prescribed shape, size, accuracy and surface finish. Detailed discussion of tooling design in ECM is given in the paper by Jain and Rajurkar, which was published long back in the Journal of Precision Engineering. Anode profile that will be obtained after electrochemical drilling operation with bare tool, because as we have already discussed, you can have the various kind of the tools. It can be a bare tool, it can be a coated tool, or it can be a bit type of the tool, and the tooling design for all the three cases will be quite different. So, I will give you an overview of what this tooling design means in electrochemical machining, which includes various kinds of operations performed in electrochemical machining. One of them is the ECD, that is electrochemical drilling. Now, this is the shape of the workpiece which you will obtain during or after electrochemical drilling has been completed. I will just try to explain it. As you can see here, this is the tool, and through this the electrolyte is being supplied, and you can see the path of the electrolyte being followed, as can be seen over here. It is the outward mode of flow of the electrolyte that we have already discussed. Now, the important thing to see here is various zones. One zone is known as the stagnation zone, which comes just below the hole through which the electrolyte is being supplied through the tool, and the zone adjacent to this zone on either side is known as front zone, where the feed and the workpiece surface both feed is normal to the workpiece surface, or normal to the workpiece and feed, they have the same direction. And then there is the transition zone, which is produced due to the corner of the tool, and this zone is quite critical and difficult to really predict theoretically. And then last is known as side zone, rest of the zone is known as side zone, where again the inter-electrode gap will be varying. It will depend upon whether tool is coated tool, bare tool or bit type of the tool. As you can see here, in the front gap, the inter-electrode gap is designated as YE, which is equilibrium inter-electrode gap. It is assumed that the equilibrium gap more or less is the same in the whole of the front zone, although it will be slightly varying due to the change in the conductivity along the flow direction or electrolyte flow direction. Then at the end of the transition zone, you can see A0 is the inter-electrode gap, and if you go further, then finally at the end it becomes AA, or in between AS or A dash S. So, this you can see here continuously the inter-electrode gap is varying, and accordingly the shape of the workpiece is also varying. So, what we do really in anode shape prediction, that we try to predict at a small interval the inter-electrode gap in all the four zones, that is stagnation zone, front zone, transition zone and side zone, and then join these points of inter-electrode gap on the workpiece surface, and then you will get the shape of the workpiece as well as the size of the profile that you have obtained on the workpiece. So, schematic diagram of electrochemical machining with outward mode of electrolyte flow that you can see here. This is the top view and this is the front section front view. So, zone 1 is the stagnation zone, zone 2 is the front zone, zone 3 is the transition zone and zone 4 is the side zone. Now, anodic dissolution from side surfaces. Now, we have seen drilling. Now, this gives just a schematic diagram how the dissolution is taking place in case of insulated tool and bare tool. Now, in case of insulated tool which is fully insulated, only bottom part is bare. So, you can see the inter-electrode gap in case of insulated tool is constant in the side gap or side zone, while same is true in case of front zone. But if you see the case of bare tool, the inter-electrode gap is continuously varying in the side zone as you can see over here, while in the front zone it is more or less the constant. So, this gives an overview of how the shape of the workpiece is going to vary in case of electrochemical drilling with bare tool and coated tool, and this is the workpiece as you can see in both the cases. So, what is the job in anode shape prediction? That we are supposed to predict what shape of this workpiece we are going to get, and if we can predict the shape of this workpiece, then we should design the tool in such a way that we get the desired shape of the workpiece after electrochemical drilling operation or for that purpose any other operation. And these figures are taken from the paper by Park, Kim and Joe in published in the year 2006. Now, let us see anode shape prediction methods in detail and what it deals with. What is anode shape prediction in electrochemical machining? Let us try to understand it first. Consider the case of electrochemical drilling as I have shown to you in the earlier slide for understanding the process of anode shape prediction. While we are trying to predict the shape of the workpiece that you are going to obtain after electrochemical drilling operation, you are given, for that matter, not only drilling operation, you can say plain parallel electrode machining or any other purpose. You are given the following things. You are given the machining conditions that includes voltage across the electrodes, inter-electrode gap, that is normally the initial inter-electrode gap, electrolyte conductivity, that is again the electrolyte conductivity at the inlet, electrolyte flow pressure, or you can calculate electrolyte flow velocity, electrochemical equivalent of anode material. Now, here you are given the feed rate also, which is not mentioned here, feed rate given to the workpiece, tool profile, because for any machining operation you are given the machining condition as well as shape and size of the tool. That means, if you are considering 2D problem, then you will be given x and y coordinates of the tool at different points. Now, using a particular method, as I have mentioned in the earlier slides, you can use one of the various methods for prediction of the anode shape. Numerical methods are like finite element method, finite difference method, empirical method, cos theta method or any other method, depending upon your acquaintance and convenience. Calculate inter-electrode gap at different points along the tool axis. Finally, these points should be joined to get the obtained anode profile. As I have already mentioned, like this shape that you had obtained in different zones. So, what you are supposed to do? You are supposed to calculate inter-electrode gap at different points. like this, and once you obtain these inter-electrode gaps at different points, then you join it to get this as the shape of the finally drilled hole. So, it will look like this, as you can see here. So, really speaking, what you are supposed to do by this, that you are, say, suppose this is the tool, and hole is there like this. So, what you are supposed to do, really you are supposed to calculate inter-electrode gap at different appropriate intervals in different zones, and once you are able to calculate these inter-electrode gap by 1, by 2, by 3, etc., then you should join them, whether this variation is linear or non-linear, depending upon that you can join these points and to get the desired anode profile. Now, not only the drilling operation, you can do the plain parallel electrodes machining. You can see here that this is the tool and this is the workpiece. Now, you are given, say, if you take the 0 feed rate, not necessarily that always you will have some finite feed rate, in some cases you can have the 0 feed rate also. You may be given electrolyte flow velocity, that is over here at the inlet, temperature, initial temperature of the electrolyte, and T1 can be the final temperature over here at the end when it is coming out, and other details are given as I have mentioned in the earlier. And so, initially the inter-electrode gap at every point will be the same, as you can see over here, and this inter-electrode gap has been discretized to solve this particular problem with the help of finite element method. Now, this is at the 0 second time. Now, once you have done the machining, then what will be the shape of the inter-electrode gap, as you can see here, that this is the initial one. Now, as you move in the forward direction or in the direction of flow of the electrolyte, the inter-electrode gap has increased, because feed rate here is 0 and material is being continuously dissolved from the workpiece. So, definitely the gap between the tool and the workpiece will keep increasing, and at different points you can see the gap is continuously increasing. How this gap is changing, this will depend upon what are the various assumptions that you have made during computation or computational experiments for plain parallel electrode machining. Now, as the time further increases, you can see the inter-electrode gap has further increased, and so in this way, when 100 second has become, this gap by 3 has become higher than the by 3 at the second stage, by 2 is also higher than the second stage, and by 1 is also higher than the second stage. And so, you can see with 0 feed rate, the inter-electrode gap is continuously increasing, but this is not really what we want. Normally, in case of electrochemical machining, we normally give a finite feed rate. So, let us assume that feed is equal to F1. Now, this feed is to be selected very carefully. The simple rule is the feed rate should be equal to the linear material removal rate. That means, F should be equal to MRRL, linear material removal rate, that we have already discussed. What is this linear material removal rate? Then you will get inter-electrode gap all the time as YE, but that is also not very true, because as the electrolyte flows along the flow direction, then temperature of the electrolyte is changing. If temperature is changing, electrolyte conductivity will change, conductivity is changing, then current density will change, and current density is changing, then linear material removal rate will be different at different point. So, really speaking, throughout the inter-electrode gap, the equilibrium gap will not be constant, rather it will be different at different points. So, you can see after a certain period of time, say 50 seconds, you can see the here the gap was same at different points, but in this particular case the gap has changed constantly, by 1, by 2, by 3, both, all the 3 are different from each other, while here by 1, by 2, by 3 like this, by 1, by 2, by 3, they are the same at t is equal to 0 second. And here also it is slightly changed, but not as much as in the particular earlier case, and this is the feed rate is F1. So, this is the way you can predict this, find out the, what you have to do here is that at every point you predict the interelectrode gap. Take many points over here, larger the number of the points you take, and then more accurate will be the prediction of the anode profile. Now, you find out this and then join them in a proper way, you will get this as the workpiece profile. Now, as I have mentioned, there are various methods of prediction of the anode shape. Many researchers have analyzed this using the numerical analysis techniques. Now, this definitely requires high speed computers. Now, what steps you are going to follow for predicting the anode profile using the numerical analysis approach? Say steps you can see here. First, decide the type of analysis you want to conduct, whether it is 1D, it is 2D or 3D. Normally, it is 2D or 3D. Then collect the initial data, that means the variables and constant values of the some of the variables and varying values of the variables, something like conductivity, initial temperature, voltage applied and so on, that we have already seen. Then perform preliminary computation. In some of the cases, you may have to conduct certain calculations before really starting the numerical analysis method. For example, you may have to calculate the electrolyte flow velocity if you are given the cross sectional area of the interelectrode gap at different points. So, there may be other calculations. If the alloy is there in place of a pure metal, then you can have built-in program which can calculate the electrochemical equivalent of the anode workpiece. Then solve the finite element problem either as a temperature distribution problem or as the electric field potential distribution problem. You find out these main variables. After getting this variation of temperature or electric field potential at different points, then secondary calculations are to be done. That means, you have to calculate the, if you have found the temperature, then you have to calculate the current density, electrolyte conductivity and so on, and finally, you will calculate the interelectrode gap. After that, calculate secondary variables such as temperature distribution, if it is a electric field potential distribution problem, electrolyte conductivity, current density, etc. Then calculate interelectrode gap along the electrolyte flow direction, as I have shown in the earlier slide for plain parallel electrode machining, or before that I have shown it for the electrochemical drilling operation. And using the computed interelectrode gap at different points, make anode profile by joining them appropriately, and that is what you call it as anode shape. The goal is to determine interelectrode gap at different nodes on the workpiece surface, and finally, to predict the profile or the shape and size of the workpiece variation along the electrolyte flow direction. Suppose it is a temperature distribution problem, then use appropriate differential equation to evaluate temperature distribution along the electrolyte flow direction. Real life problems are not as simple as plain parallel electrode problems. They are very complicated, interelectrode gaps are there, and in those cases you have to go, if you want to predict it accurately, for numerical analysis techniques like finite difference method, finite element method, boundary element method. And then from the above temperature distribution, calculate electrolyte conductivity at different points, because electrolyte conductivity is a function of the temperature of the electrolyte. After that, find the effective feed rate at different points, because as I mentioned earlier, that suppose this is the workpiece and tool is being fed normal to the workpiece surface, then feed rate will become whatever is the feed rate of the tool. But if the workpiece is inclined like this and tool is being fed like this, then you have to calculate what is going to be the feed rate at different points of the workpiece, if it is curved one or having different curvature, and then F will not be equal to the actual F t that you are giving, but it will be a component of that. So, you have to calculate effective feed rate at different points. Assumption. Now, how to calculate this effective feed rate I have already discussed while discussing the theory of electrochemical machining. Here you are making the assumption that Ohm's law is followed. That means, while computing the current density at different points, you are assuming that the current flow lines are straight and perpendicular to the surface of the workpiece. Using J, after calculating the current density, calculate inter-electrode gap at different points along the electrolyte flow direction, and this may be any shape of the workpiece. And after finding out the inter-electrode gap at different points, plot anode shape from inter-electrode gap by joining these inter-electrode gap at different points. Now, there are certain limitations of this particular method, that Ohm's law is obeyed, which is really not true, especially when inter-electrode gap is not plane parallel, as in case of plane parallel electrode machining, then Ohm's law does not hold true. Lines of electric field potential are not always straight and normal to the electrode surface, especially when a curved zone is analyzed, then Ohm's law does not hold true. Hence, the solution of Laplace equation is always recommended, and it is the reason why researchers have adopted finite difference method or finite element method or boundary element method. Now, when you are using electric field potential distribution method or numerical analysis is being used, then calculate electric field potential by solving Laplace equation in 1D, 2D or 3D, depending upon which problem you are solving. Now, just like the given here in 3D, del 2 phi over del x 2 plus del 2 phi over del y 2 plus del 2 phi over del z 2 is equal to 0, and initial conditions are phi is equal to 0 at the cathode and phi is equal to E V is equal to A V minus delta A V at the anode, where A V is the applied voltage across the electrodes and delta A V is the over potential that exists at that particular point. So, you can find out from these two data the effective voltage E V. Now, then calculate the current density J. Using this equation, after finding out the current density, you can calculate the temperature distribution along the electrolyte flow direction, that is the x axis. Here it is assumed that the electrolyte is flowing along the x axis. That is why you have here del T over del x is equal to V minus delta V square divided by U 0 rho E C E by 0 square is equal to A k. Now, here you can see that here k is missing. So, you can see that this is the delta like shown over there, delta V. So, you can see here that except k, all other terms can be considered as constant in a very small area or zone rather, because here what we do, that when you are using finite element method or finite difference method or boundary element method, the size of the elements is very very small, say less than a millimeter size of the element. Then in that particular small size of the element and for a very short period, say less than a second or 1 second, the change in the flow velocity, electrolyte flow velocity U 0 will be negligible. Same way, change in the specific heat C E of the electrolyte over this region will be negligible, and change in the inter-electrode gap will also be very small. That is why all these parameters can be considered as constant, and K is the conductivity of the electrolyte. So, find the temperature at different nodes points and use it to modify electrolyte conductivity, that is K, and we already know that K is equal to K0 1 plus alpha delta T, that I have already explained, or if you are taking into consideration a white fraction, then it becomes 1 minus alpha V raised to power n. You can check it from the notes, and then you can calculate this, and then you can find more accurate temperature distribution along the electrolyte flow direction. Then compute the current density at different points, and after computing the current density, compute the interelectrode gap at different points. Connect these interelectrode gap points and predict the anode shape, as I have already explained. Now, same procedure which I have mentioned is shown over here in the flow chart. Flow chart for anode shape prediction procedure using finite element method. Now, when you are starting it, read the given data and print input data. Given data includes all machining conditions and tool profile, and that is x, y or x z or y z coordinates of the tool. Then general nodal coordinates, then you have to discretize the interelectrode gap, that is the gap between the tool and the workpiece, as I have shown over there earlier. You have to discretize it into the different parts depending upon like 1, 2, 3, 4, and then coordinates of 1, 2, 3, 4, 5, 6, 7, 8 or whatever is the discretization, then you have to generate automatically with the help of the software the coordinates of different points, because there are maybe hundreds and hundreds of points for which you have to generate the coordinates and which have to be analyzed. It is not only 5 or 6 points. Then generate the stiffness matrix. This can be understood by those who know or who have the idea about the finite element method. You have to develop the stiffness matrix and compute number of computation cycles required to drill the hole or to machine the workpiece surface. Then compute feed rate in different zones, as I have mentioned in the earlier slide, that if the feed rate is not normal to the surface of the workpiece, then the feed rate direction rather is not normal to the workpiece surface, then you have to calculate the effective feed rate at different points which are to be analyzed, just like points 1, 2, 3 in this particular 1, 2, 3, 4 in this particular case. Then apply boundary or initial conditions, as I showed you earlier also, just like phi is equal to 0 at the cathode and phi is equal to B minus delta V at the anode, and there can be there will be other boundary conditions also. Then solve the equations, that is the Laplace equation, to evaluate the potential distribution or temperature distribution at different nodes. Then compute the change in the electrolyte temperature at different points. After computing this, compute electrolyte conductivity. Now, if feed rate is 0, then compute y for 0 feed rate. If feed rate is not 0, as I have shown to you, that means f is not equal to 0. Then compute y, that is the interelectrode gap for finite feed rate at different nodes. Find the current density again. Compute linear and volumetric material removal rate. Then reassign y coordinates for side flow, because this process will be different for plain parallel electrode machining or electrochemical drilling or other kind of the complicated shapes. So, you have to change this procedure slightly depending upon the type of the workpiece. Then modify V for new values of these one, check if machining cycles are complete, for new values of interelectrode gap, y is the interelectrode gap. Now, if here I have shown 3 stars, this indicates that if suppose total time required for machining is 100 seconds and by the time you come over here it is only 50 seconds, then you have to again go back to the earlier one where I have shown it 4 stars, go to that particular point and then again redo the whole thing for the new coordinates of the different nodes and then recalculate the potential distribution, temperature, conductivity, inter-electrode gap and so on. And this process will keep going on unless all machining cycles are completed, and then after that you print the results and then end and then stop. So, this is the procedure that you can follow for prediction of the anode shape in case of ECM using finite element method, boundary element method or finite difference method. Now, this is the numerical analysis method that I have explained to you. There are various other approaches for anode shape prediction in ECM that have been proposed by various researchers. The basic reason is that it is really difficult to accurately predict the flow lines or electric field flow lines in the inter-electrode gap, and then making all these calculations becomes cumbersome. So, many researchers have proposed empirical approach which are or nomographic approach which are much simpler than these numerical analysis approaches. So, some of these approaches I am going to discuss in this particular case. Now, let us discuss some of the other approaches proposed by the various researchers. Empirical approach which tells you really the inter-electrode gap and some of the zones, and these equations which are empirical in nature have been proposed based on very limited number of experiments, and the caution to be observed here is that these equations are applicable only for those workpiece material, those machining conditions and to some extent those tool material also. So, they cannot be the generalized approach. And second thing, one has to be careful that most of these researchers have proposed only inter-electrode gap in either one zone or two zones, not in all the 4 zones, as we will see as we proceed. So, exact path of electric current flow lines within a complex inter-electrode gap is difficult to determine analytically, that we have seen and I have mentioned. Empirical equations suggested by Koenig and Paul of Germany to evaluate inter-electrode gap A0 at the start of the transition zone is given as follows. That is, A0 is equal to RC raised to power 0.35 multiplied by 0.35 into 10 E multiplied by y whole raised to power 0.5. Now, here RC is the tool corner radius, YE is the equilibrium gap, and this equation is applicable for YE greater than 0.15 and less than 0.6 millimeter, and RC, that is the corner radius, should be greater than or equal to 0.5 millimeter and less than or equal to 5 millimeter. These were the conditions under which various experiments were conducted by Koenig and Paul, and they proposed this particular empirical equation for that purpose, and E star is the Euler number which is constant. For the case of tools partially or fully coated on side wall and having RC greater than or equal to 1 millimeter, less than or equal to 5 millimeter, that is tool corner radius, Koenig and his group proposed another equation, that is A0 is equal to 0.1 plus by E multiplied by 0.314 RC plus 1.17 for BB is equal to 0, that is bare bit length of the tool, and for YE greater than 0.1 and less than or equal to 0.7 millimeter. BB is nothing but, say suppose this is the tool and whole of this tool is coated with the insulated layer. That means, it is like this, right. So, that means whole of it is coated, machining is being done by this front area of the tool only, not from the side. Now, if BV is greater than or equal to 1 millimeter, then this is the equation that they have proposed. That simply means, as you can see here, that say suppose this is the tool, then this is coated up to this particular point, and this bare length of the tool, this is known as BV, bare bit length, and this should be greater than or equal to 1 millimeter, then this particular equation holds good. Above equations are reported to yield erroneous results at low feed rate. Now, there is another parameter which affects all these equations, is the feed rate. If feed rate is very low, like 0.006 millimeter per second, and if equilibrium gap is large, greater than or equal to 1 millimeter, then these equations do not give very good results. Another point to note here is, as we had seen earlier, that there were 4 different zones, and in the side gap there were 3 different kind of inter-electrode gap, depending upon how long is the coating on the tool. But here they have proposed only one simple equation for one particular inter-electrode gap. So, really speaking, this kind of approach cannot be applied for anode shape, full anode shape prediction. However, it can give you inter-electrode gap in a certain zone only. This is the paper which we have referred for this. So, you can see here various zones. I am repeating this figure. Now, this is the A0 for which they have proposed the equations, but and this is the A0 at the start over here at the transition zone, because here the transition zone is ending. So, it is just over here. Now, the question arises, what about A dash S, what about A over here. So, really speaking, this equation approach, empirical, this particular approach cannot be applied for prediction of complete anode profile. Same way, Jain and Pandey also proposed one equation, again the same way that they have proposed this very simple equation for the prediction of inter-electrode gap in the beginning of the or end of the transition zone. Again the same weakness over there, RC1 and RC2 depend on many factors like tool and work material combination, electrolyte, etc. Equation to evaluate AS and AS dash in the side zones under coated and bare part of the tool are missing. Later on in the same paper, they have given the equation for AS, that is given over here, that is AS is equal to 2 BB, that is the bare bit length, multiplied by E plus RC raised to power 0.7 into 0.12310 E star multiplied by E raised to power 0.5 and 0.65 by E. Now, AS dash, as I showed in the earlier slide, that AS and AS dash were missing. So, this is the equation which they proposed for the prediction of inter-electrode gap in that particular zone, and this has been reported in this particular paper also. So, what it shows that again there are so many assumptions, because AS and AS dash may not be constant in the whole zone, and if you are following numerical analysis technique that I have already explained, then you can predict these side gaps A0, AS dash much more accurately than with the help of these equations, but these equations are good enough for approximate prediction of anode profile. Now, there is another approach that is known as nomographic approach, where again this was proposed by Koenig and Paul in the beginning, when this ECM process was getting more and more popularity, because such approach are very easy to apply, especially by the industry people. Now, here you can see 3 nomograms are given. One, in this particular AG is nothing but the inter-electrode gap Y, and you can see here R is the tool corner radius. So, this one gives the relationship between the various tool corner radius and inter-electrode gap. Then again here this one is for the, you can see bare bit length given over here, and this graph will give you the value of AS. Now, what you have to do, I have explained here in different line. For the calculated AG, that is the inter-electrode gap, and R, that is given over here corner radius, find point A. Now, suppose we are given here 0.35 as the inter-electrode gap, and there is certain say 2 millimeter as the tool corner radius, then you get the point A. Now, a line parallel to the x axis which cuts at point B is drawn from point A. So, you will get the point V over there. Our objective is to find out the value of the AS for this particular conditions. Then, for AG, that is the inter-electrode gap, and bare bit length BV, that is given over here, as you can see, find point C, from C draw a line parallel to this. Now, what you have to do, we are given this inter-electrode gap already that we have taken over here, same inter-electrode gap, draw a vertical line and then take the bare bit length over here, that is 0.7 millimeter, wherever it cuts, you from here you draw a line parallel to the x axis, you will get the point D. Now, what you can do, you join the point B and point D such that it will cut at point E on the middle nomogram. Now, when it cuts at point E, just see to the x axis to cut it at point D, then now join D and B, join this particular point and this particular D and B. So, it will cut it to cut at E, find point F from inter-electrode gap, draw a vertical line. This is the inter-electrode gap that we already know, because here also we have used, here also we have used. From here draw a vertical line. Now, after drawing the vertical line from F, draw a curve parallel to the plotted curve to cut vertical line at G. From here, from this point E, this is sorry not F, this is point E. From point E, draw a curve parallel to this particular, because you can see various curves are plotted here. From point E, wherever it is cutting, you draw a curve parallel to this and draw a vertical from point F. So, both of them will cut at point G. Now, at this point G, you can find out, you can rather interpolate, because we know this point G lies between AS of 1 millimeter and 1.2 millimeter, sorry, this is 1 millimeter, this is 1.1, this is 1.2. So, this lies between 1 and 1.1. So, from here you can find out what should be the side gap at point G, and so with the help of this you can predict the side gap, and that is shown over here. That is their objective, because this side gap will be constant, because the tool is coated more or less fully coated, except a very small part that is shown here by BV, and that we have assumed here as 0.75 millimeter. So, for this kind of the tool we can find out what is going to be the inter-electrode gap AS, and this inter-electrode gap is nothing but the overcut in the side gap. So, you can predict, except this small part here, overcut in the side gap can be predicted by this particular method, and it is very simple to use on the shop floor. If you are given, or if you know the interelectrode gap, if you know the tool corner radius, if you know the bare bit length, all these are known in advance, then you can predict what is going to be the side gap for the given machining condition. Mind it, if machining conditions are changed, then this side gap is also going to change. So, again this was taken from the paper by Koenig and Paul. Now, cos theta method, as I have mentioned, can be used for anode shape prediction as well as for tool design purposes. So, what I am going to discuss is, I am going to discuss this cos theta method for tool design purposes. This method was proposed by Tipton. Now, there are certain limitations of this cos theta method, that it is applicable when angle between feed direction and normal to the workpiece or tool surface is gentle. That means, no sharp corners are there. This method was proposed by Tipton. It is not applicable in case of sharp corners. It is applied for 3 regions, as we will show it, for theta is equal to 0 degree, theta is equal to 90 degree, and theta somewhere in between 0 and 90 degree. Figure will be shown in the following slide. Now, here IEG, that is interelectrode gap, is abbreviated as Y suffix E, and for theta is equal to theta greater than 0 degree and less than 90 degree. Interelectrode gap parabolic in shape if theta is equal to 90 degree. If theta is 90 degree, that means the feed rate is 0, just like I will show you the example. Suppose this is the tool and this is the workpiece over here. Now, here normal to this, the workpiece surface, and feed direction is this. So, the angle between this and this becomes 90 degree. When this angle theta is 90 degree, then the shape of the workpiece that you are going to get will be parabolic in nature. This is the shape of the workpiece that you are going to get, parabolic in nature after electrochemical drilling. And this shape we had discussed while discussing theory of electrochemical machining also. So, cos theta theory is not applicable to regions shown by dash dash dash. I will show you in the next slide. Assumption here is that current flow lines are straight, parallel and normal to the work, tool or both surfaces. That means, Ohm's law is being followed. It assumes tool and workpiece surfaces are uniform in z direction. That simply means that only 2D problems are solved by this particular method. Let workpiece surface be expressed as y is equal to f x, where x y is the function of x coordinates. Now, point A on workpiece transferred to point B on the tool. Let us see it here. These are the 3 zones which I mentioned in the earlier slide, that one is the here where y interelectrode gap is equal to the YE equilibrium gap, and this is the one, this is the tool and this is the workpiece, and this is the parabolic surface that it is going to get if the normal to the workpiece surface and the feed direction, they are having the they are in the same direction. And then if this theta is less than 90 degree, here it is 90 degree, if theta is less than 90 degree, then you are going to get interelectrode gap or as by E over cos theta. That is what is shown over here. Now, let us see on the right side what it says, that point A on workpiece transformed to point B on the tool. This simply means, suppose this is the workpiece A and we are designing here the shape of the tool based on the shape of the workpiece that we want. So, it says that for this particular condition, point A is transformed as the point B. That means, point B will give the surface workpiece surface as point A. Now, here the coordinates of A are x, y and coordinates of B are x 1 y 1, and y is increasing in this particular direction and x is increasing in this particular direction. This is the point to be taken care of, which is shown over here by the feed direction. So, this we have to keep in mind while discussing this particular method. So, here I have reproduced the same figure. You can see y minus y 1. So, this is the y and y minus y 1 becomes a b cos theta. A b is this particular line, a is here, b is here. So, a b cos theta becomes this particular interelectrode gap, equilibrium gap, a b cos theta, and a b is nothing but by e over cos theta into cos theta. So, you get by e. Same way x 1 minus x becomes a b sin theta, that is this one, a b sin theta, and a b we know by e over cos theta multiplied by sin theta. So, we get by e over tan theta. And we know that any curved surface on y x axis dy over dx is given by tan theta, that is shown over here, dy over dx, that is given by tan theta. So, we can write y is equal to y 1 plus y e from the equation 1, that is this one. Now, we can also write from equation 2 that x 1 is equal to this one. This equation can also be written as x 1 is equal to x plus y e tan theta, and tan theta can be replaced by dy over dx. So, that is given over here. So, x 1 becomes x plus y e dy over dx. And we know as we have in the beginning said that y or the y is the function of coordinate x. So, we can assume a particular profile of the workpiece. Now, so we can write down here these equations by e is plus by 1, that is this equation can be written as by e plus y 1 is equal to f function of x, that is the that we can write from this equation like this, x 1 minus y e dy over dx. So, this is the equation 5 we obtained from these equations. Now, let us assume suppose the workpiece surface can be approximated by a series of parabolic arcs. Y is equal to a plus b x plus c x square. Okay.